So in the next section, we learn here about potential energy. And in particular, in this section, we're going to do gravitational potential energy. Okay, potential energy is associated with the position of the object within some system. So it's a property of a system, not of an individual object. Okay, a system usually contains maybe more than one object. So it's the position of an object with respect to another object. Okay, or with respect to several other objects. So a system is a collection of objects interacting via forces or processes that are internal to the system. That has to do with potential energy. So we talked in chapter 4 about conservative and non-conservative forces. And for every conservative force, you can define a potential energy function. Okay, so conservative forces are associated with a force field. And depending on where the object is in the field, it has a certain potential energy. Okay? So evaluating the difference of the function at any 2 points in the object's path gives the negative of work done by the force between those 2 points. And we'll see that in a minute. So gravitational potential energy, what's our system, first of all, in this case? We have gravity is our force field. So gravity in terms with reference to the Earth, when you're close to the Earth's surface, you're talking about a system that contains the Earth and our object of interest, whether it's a person or it's a book or some kind of object. Yeah? So it's the relative position of that object with respect to the Earth. And we can define any position, any configuration as our zero potential energy. It's common to take that zero potential energy at, say, the surface of the Earth. So right, we're standing. So if we lift an object above the surface of the Earth, it automatically gains gravitational potential energy then. Okay? So here's an example. Here's the surface of the Earth where we define our potential energy to be equal to 0. So we can write that here. Our potential energy reference equals 0. At this point, okay? And as you lift an object up, say till here, it gains a potential energy. And how much energy does it gain? That depends on the height it has risen. So if that height is some final yi, let's say some initial position, then some distance y, then we have done work against this gravitational force, which is mg, and we have lifted it a distance of y. So mg times y is going to be the work done, which is going to be the amount of work that we need to do to lift this book. Since it's a conservative force, we can recover all of that energy, yeah, that went into doing the work. So mgy or mgh, as this is conventionally, the height is written as h. So you might see the formula mgh. In this example, it's mgy, y being this entire distance here. That's the potential energy for this book at this higher position. Now, let us say you let go of the book at this position, and this is its initial position, and it's going to fall. And let's consider a position while it's falling as its final position. So then the new height at this point is this height, yf. Yeah? So the amount of energy that it has lost, or the work that it has done to fall from here to here, is the change in height, delta y times mg. Yeah? And delta y is yf minus yi. So mg times yf minus yi, and it's the negative of this. So if the book is falling downwards, then yf is lower, a smaller number than yi. This term will turn out to be negative, and the work done will be positive. Since the force and the displacement are both downwards, the work done by gravity will be positive. Huh? Okay. And that work will be in joules, just like energy is in joules. So work and energy are interrelated, very closely related. Okay. So what did we say? We said that we need to define a reference level for gravitational potential energy. That's where we set our potential energy to be 0. You can define it to be anywhere in your problem, but once you set it, you cannot change it when you're doing your calculations, okay? So a location where the gravitational potential energy is 0 must be chosen for each problem. The choice is arbitrary, okay? Since it's the change in potential energy that we are most interested in. Once the position is chosen, it must remain fixed during the problem. Choose a convenient location for 0 reference height, often the Earth's surface, but sometimes it may be some other point, okay? So we come to an important concept in this chapter, which is the conservation of mechanical energy. Okay, what is mechanical energy again? It's the total sum of the kinetic and potential energies that a system may possess. Yeah? So conservation in general means that you have the same value or same number at the start and some kind of final position. Yeah? So if you start with a given energy, let's say 50 joules, then at any point that you choose to look at the system, that your final position, maybe in time or in configuration, it must have the same 50 joules of energy, okay? So let's read this green statement here. In any isolated system of objects interacting through conservative forces, only through conservative forces, the total mechanical energy of the system remains constant. So there are a few important things here, and I just want to highlight them for you. One is isolated system. Okay, what does that mean? An isolated system means that you do not have any exchange of energy or any kind of interaction with whatever is outside the system. Okay, so the only interactions occur within the system. That's important. No energy can escape from this system. No energy can come into the system. Also, notice that the objects are interacting only through conservative forces. That means we have no non-conservative forces, no dissipative forces, no frictional forces, no loss of energy possible, right? In such a case, we have the conservation of total mechanical energy. Total mechanical energy is the sum of my kinetic energies plus any potential energy or energies in the system. This together is my total kinetic and total energy for the system, sometimes written as TE for total energy. Yeah? Okay, so let's look at this. What does it mean? It means that if my total energy at some initial position is this, energy EI, then at a final time or final position, that energy EF must be equal if my energy is conserved, right? That means if the two conditions hold, that my system is isolated and my system has only conservative forces. Now, mechanical energy is the sum of kinetic and potential energy, so I can break this term down into its constituent terms. Similarly, I can break this into its final kinetic energy and final potential energy, okay? So in general, if you're solving problems which are about the conservation of energy, you need to do this. You need to define the system, include all the interacting bodies in the system, verify that there are no non-conservative forces, okay? So we've verified our two conditions. Now, select a location for zero potential energy for gravitation, typically where the height equals 0, where our ground is. Do not change this location when you're solving the problems. You must measure everything, all heights from this or any depths from this location. Select your body of interest. It might be an object that's falling or rising or whatever. And identify 2 points of interest. One point will typically be where all the information is given, like, the height, its energy. And the other point will be some other position where you might be asked to find out a certain value. So typically in energy conservation problems, you have two different positions for the system. Then you're going to apply the conservation of energy. What is the total energy at the start, equated to the total energy at the end, to try to solve for the unknown quantities. Yeah? The unknown quantity might be a speed or a position. You're going to just substitute in the known values and calculate for the result. Okay? What happens when you have non-conservative forces? So then our work energy theorem changes, it gets modified. If non-conservative forces are present, certain amount of energy is used to overcome them.